All right, so let's talk about um, linked lists. All right, so let's actually open up, and I'm going to actually write, because now you have an Android project. Well, I'll write it inside of Android so you have a starting point, but I'm actually not going to write much of the interface. You'll have to do most of the interface yourself. Um, so what we did today is we worked with an array, right? So we had an array of text views or whatever they're called, and one of the limitations we put on ourselves is we said, well, the maximum number of buckets is 1,000, right? So if I'm going to put any more than 1,000 text views into this, I'm screwed. I can't support it. We probably weren't going to put 1,000 in there, but the point is we had to get a whole bunch of memory to hold 1,000 of those guys, even though we didn't use most of it. Okay. So having said that, let's talk about the pros and cons of arrays, and then let's talk about what might be better under certain circumstances. So we would say that arrays, first of all, arrays use contiguous memory. Did we talk about that last time? Well, let's just say it again. So arrays use contiguous memory. What does it mean when I say an array uses contiguous memory? Like, how are they implemented? Memory in a row. Contiguous means memory right next to each other. Okay? So when we say something like int array AR is equal to new int array 25, that's going to give me 25, it's going to give me, an int in Java is 32 bits or 4 bytes. So this is going to give me 100 bytes in memory right next to each other to hold 25 integers in 4-byte chunks. Make sense? And it puts them right next to each other in memory for a very important reason. Okay? And that reason is for speed. So if we kind of draw this, and it's pretty important that we do this in a previous class. So actually let me, just for time, I can use this slide to show it. Okay, so this is from earlier computer science programming class in undergrad, but MSIT, you kind of take sophomore, junior level computer programming at the master's level, just the way we have it laid out. So in any case, an array, when we create an array, here's the elements of the array. This is bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, and those guys are right next to each other in memory in 4-byte chunks. So 100, 104, 108. Why is it 4 bytes? Because these guys are integers. If it was a char, it would be in 2 bytes. 2-byte chunks, 16 bits. Okay? And here's the actual values that are there. And we say that arrays are fast because we can actually calculate the position of something in an array. So for instance, when I say AR at bucket 2, I'm actually saying go to the base address of AR, which is 100. Add to it 2 times the size of an int, which is 4. So 2 times 4 is 8. 100 plus 8 is 108. That's where bucket 2 lives. Is at memory address 108. Make sense? So we can calculate the position in memory where that value lives. Okay? So because of that, that's how arrays structurally work under the hood. So because of that, we would say that arrays are fast. We would also say that arrays are memory inefficient because they require a whole bunch of memory, but more importantly, require memory right next to each other. So for instance, if you want to store 1,000 integers, well, say let's keep the number simple. We wanted to store 25 integers. We needed 100 bytes. Now, 100 bytes isn't that much memory, but let's say we were almost out of memory in our computer. And we only had 92 bytes in a row. We had 130 total bytes free, but only 92 in a row. We actually couldn't store that array. We didn't have enough contiguous memory to store it. Make sense? So arrays have that limitation. realistically today, we have lots and lots and lots of memory, so only in extreme circumstances is that going to be a real issue for us. Okay, the memory inefficiency issue. So we just got tons of. I mean, this machine has 16 gigs of RAM in it, and I was upset that I could only put 16 gigs of RAM in it. You know, the Apple's newest MacBook Pro wouldn't let you upgrade beyond that, which is this is soldered in there. It's ridiculous because there is no upgrading it at this point. I have to just get a new machine. So in 2 years, when 32 gigs might be more necessary for some things, I can't upgrade. It's dumb. But in any case, we have lots of memory. So that's probably not going to be a problem most of the time. But arrays are fast. They're memory inefficient, and they're also inflexible. Which means when we build an array to be a certain size, 25 buckets, 25 elements, and I want to put 26 elements in it, I need to rebuild the array. I can't just expand it. Okay, so think about it like a house. If you build a house and you decide you want to put a porch on it, like a deck or something like that, you can't just add the deck in array language. Instead, you have to build a brand new house that's a mimic of your first house that has a little bit more space in it so you have room for the deck. And then you burn down the old house and move all your furniture over to the new house. Not very efficient, right? In real life, what do? We just build the deck, take up some of our yard. So arrays are memory inefficient from that perspective as well because they are inflexible. We build them to a certain size, and that's the size they are forever and ever. Okay? Would you say that it's a fairly common thing for us to want to store collections of information, but we don't necessarily know how many pieces of information we're going to store? I mean, we had it in this homework assignment, right? We didn't know how many different elements they were going to add. Could have been 1, could have been 20, could have been 300. So what did we do? We just built an array capable of holding 1,000 and hoped that it was enough. Well, so what are we going to do here? Well, we possibly look at something that gives us more flexibility, possibly at the cost of some other stuff. So we come in here, and we have something called a linked list. We have this larger classification, something called data structures. All right, so a data structure is a structure for holding data. Kind of a cop-out type answer. Now, the reality is we have this idea of traditional data structures. So these are things like linked lists, stacks, queues, trees, graphs. These are our traditional academic kind of data structures. Now, and these have been around for years and years and years and years. The reality is that when we think about specifically object-oriented languages, almost anything's a data structure now. I mean, we create an object for holding a couple pieces of information. We might have an object for a fraction that holds the numerator and denominator of a fraction, and they can do stuff, operate on that fraction. That's a data structure, isn't it? It's a data structure specifically built for holding fraction information. Now, it didn't make this list of traditional data structures, but it's still a data structure. So don't get too caught up in that name, data structures. Okay? It's just stuff. They're just tools. Like we walk into Home Depot, we buy something, and they help us solve problems if they happen to be the right tool for the job. All right, so the one we're going to look at first here is this thing called a linked list. So we'll call a linked list at the generic level a competitor with arrays. Okay, so a competitor with an arrays. Now, one important thing to kind of just remember here, even though I promise you our next homework assignment deals with linked lists, linked lists aren't better than arrays. They're not the upgrade. Notice I said competitor here, not upgrade. So even though typically you learn arrays before you learn linked lists, you're still going to use arrays a lot. If you know how many elements you need to store, if you know you exactly need to store 10 elements, for example, why wouldn't you want the speed from an array? Just makes sense. right? But if you don't know how many elements you're going to store, and you need that flexibility to be able to kind of have something grow and shrink, a linked list is pretty helpful. So linked lists kind of has the opposite properties of an array. We would say linked lists are very memory efficient, but they're relatively slow. All right, and the reason for that is they do not use contiguous memory. That's why they're so memory efficient. It's because they don't rely on the elements that you're storing to be right next to each other in memory. If you need to hold 100 bytes of information and you only have, you have 130 bytes total of free memory, but you only have 20 in a row, linked lists will work. You don't need them to be next to each other. You just need to have a space for them somewhere. Okay? So they're relatively slow because we can't compute a specific bucket, which means that we have to traverse a list from beginning to end or from end to beginning. Okay, so lists have entry points. So let's look at a list as an example. Let's actually look at implementation here first. So a linked list is going to be a collection of nodes. Now a node is going to have a payload. This is the stored value for this bucket of the list, and can be, let's just leave it at that. I don't want to go any farther than that for it right now. So it's going to have the payload, and then it's also going to have a node. We'll just call it next node. This is a pointer to the next node in the list. Okay, so our linked list is made up of a whole bunch of little nodes that are linked together, hence the name linked list. One node knows how to get to the next node. That guy knows how to get to the node after him. That guy knows how to get to the node after him. And the very last node knows that he goes to oblivion, that there's nothing after him. Okay, that's the end of the list. The end of the list is a node whose next node is null. Now, the beginning of the list, we have this variable called head. So let me just leave this over to the side for a second here. So when I have the empty list, that is the list containing nothing, we have a variable called head that points nowhere, points to nothing. All right, so let's go ahead and start a new Android project here. All right, so we'll start a new Android Studio project. We'll call this CSC537 Fall 2017 Homework 2 template. All right, keep all the other settings the same. We'll have an empty activity. Call the guy main activity, that's fine. I'm actually not going to do much with the interface here. We're just going to write some objects. Okay, so what I'm going to do here is I'm going to go ahead right off the bat. I'm going to create a new class. And we're going to create a class called node. Okay, so here's my node class. And we decided that a node is going to have a payload. Now, our homework assignment is going to have you working with numbers. Okay, we'll talk about that in a bit. So to give you a reasonable starting point, our type of payload is going to be an integer, an int. Okay, so we're going to have private int payload. So the kind of value a node will hold is a single integer. And then we're also going to have a private node next node. So node will know what value it holds, and it will know how to get to the next guy. Make sense? Okay. And we'll make both of those private for right now. Then we need a constructor for our node. So we'll say public node. What's who? Node is the guy I'm creating right now. So this is a variable named next node of type node, the guy I'm building right now. So a node knows about another thing that's like him, just like I know about you. You're another person. Make sense? All right, so to build a node, maybe we take in a payload. We'll say this dot payload is equal to payload. This dot next node is equal to null. So when we build a brand new node, we give it the number, the value we want it to hold, and we set its payload equal to that value. And then we also, by default, set his next node to nothing. But we need to have the flexibility of updating his next node later on. Okay? So we'll kind of add some of that ability in here in a few minutes. So leave it like this for a second. So that's what node's going to look like. Now I'm also going to add a Java class. We'll call this guy linked list. All right, now I'll throw this out there. It's in the homework assignment that I'll put up there at the end of class. But like I mentioned earlier, when you're doing the homework assignments in my class, you can only use things that I've introduced. All right, so I specifically say it in the wording for the homework assignment, but there is a linked list built into Java. You're not allowed to use it yet. You got to write your own for now. Okay? Once you've had some practice, I'll show you the one that's built in. For right now, you got to write your own linked list. I'm giving you the starting point for that. All right? So public class linked list, we're going to have a private node head. This guy points to the beginning of the list. Now, when we first build a linked list, the list is empty. There's nothing in it. So head would actually be equal to null. So public linked list, this dot head is equal to null. All right, so here's a simple implementation for a linked list that can't do anything other than just exist. Okay, so this linked list keeps track of the front of the list. That's what a linked list does. It remembers where the beginning of the list is. And then each node knows about the next guy, knows about the next guy, knows about the next guy. All right, so if we can get to the beginning, we can then traverse the list to walk down it. All right, so if I build a blank linked list, it's going to be null. If I go ahead and I teach a linked list how to display itself, so maybe public void display, I would ask the question if this dot head is equal to null, maybe do a system.out.println empty list, like that. Else, harder stuff, because you have to traverse through the list. All right, but just for a testing scenario here, that's our linked list. So if I come into main activity here, and I just happen to use onCreate, I'll go ahead and say linked list LL is equal to new linked list. And then I say ll.display, it should print out empty list. Because here I'm creating a new variable named LL of type linked list. I'm calling upon the constructor that I wrote right there. What does that constructor do? That constructor sets head equal to null. Then what am I doing? I'm asking my LL to display itself. What does display do? Display asks the question, if head is equal to null, print out empty list. All right, so this is not a real functional linked list at this point, but it's the kind of the skeleton that we're gonna work with. So if I go ahead and run this, this program, we'll get printed out to the console empty list. that I indeed have a linked list that doesn't have stuff in it, but it's an empty list nonetheless. And then we'll figure out how to put stuff in it. All right, so there's that default hello world. If I go to Android Monitor, somewhere in here we'll have, there it is, empty list. All right, there's our empty list. Notice how much crap gets printed out there. That's why we like putting stuff onto labels and things like that rather than having to look through it in the output here. But then there would be less work for you to do. Right? All right, so let's think about what it means to add stuff to a linked list. So right now, this is what our linked list looks like. It's empty. Now, if I want to add something to the front of my linked list, all right, so linked lists typically have multiple functions associated with them. So maybe we do add front, add end, add at index, stuff like that. So if I want to add something to the front of my linked list, I might create a new node. Maybe this guy has a 3 in it. All right. And remember, when we first create nodes, nodes have a pointer to the next node that's pointing out to nowhere initially. Right? So this is my new node. And if I want to add him to the front of the list, the picture will end up looking like this. Now, if I want to add another guy to the front of the list. So in this first case, when I added this guy to the front of the list, because head currently pointed nowhere, I was able to just set this guy equal to head. Right? So we come in here, go into linked list. Let's go ahead and add a function. So we'll say public void add front, and we'll have this guy taking a payload. Now, right off the bat, we need to go ahead and build ourselves a node out of that payload. Good thing for us is we already wrote a node class that takes a payload as a parameter and builds us a brand new shiny node. Okay? So I'll come in here, I'll say node temp, or we call it n, that's good enough, is equal to new node, and we'll pass it our payload. So there's our brand new node. So when I'm adding a node to the front, I'm going to first build a node. I have my node. Now I need to add it to the front of this list. So how do I add to the front? Well, the simple case is this. I'll ask the question, if this dot head is equal to null, then this dot head is equal to n. Easy peasy. Nothing currently in the list? This guy now is. The head points to him. Now, if we're in the else here, though, that means there is already at least one thing in the list. Make sense? So now we have a picture that looks like this. If I say add front on this guy, and head points to something other than null, at the end of the day, I want head to point to this guy, and I want this guy to point to what head currently points to. So the very first thing I need to do, this is n, right? So we created that variable n, our node. It's the very first thing that happens in here. Node n equals new node payload. And that's the guy we're trying to add to the front of the list. So here's n. I need to make n's next node point to the same place head points to. Then I make head point to him. What happens if I make head point to him first? Yeah. I can't point to this guy anymore because nobody points to him. We've lost the cable. He's floating into outer space. Automatic garbage collection is going to clean him up. So in this case, the order was very important. I needed to, since, well, I still had a tether connected to this guy, I could take N and make them point to the same thing head points to. Then I'm free to disconnect this tether and hook it up into N. Make sense how important the order is there? It will be very helpful for you to draw pictures when you're working with linked lists. Okay? They are not hard when you draw pictures. Nothing we've done here so far is hard. But I guarantee the second you start working with memory, you're going to start feeling intimidated. Even though you won't have to manipulate one memory address. You just have to know that these guys are little tethers. Okay? And you're in this vacuum of space. And if you don't always have some dude attached to this astronaut here, he's going to float off. And you won't have access to him. So whether you want to think about it as scary memory addresses or the rope holding the astronaut to the space shuttle, it doesn't matter how you want to think about it. You don't want to lose it. There should always be at least one rope attached to all the pieces that you want to be able to get to. Okay? If you ever find yourself detaching a rope, bringing it down to zero, you better have a good reason for it. Probably because you wanted to remove something and they're done with it. You don't need it again. But if you need it again, you probably did it wrong. Okay? So, we just saw the order of operation there. So, if it's not the empty list, then what do? I take my new node and I set his next node equal to whatever head currently points to. So now if I go into node here, notice that next node I made a private variable. So we cannot directly access it. So we're going to have to give ourselves a setter. Have the ability to set the next node. We're also going to need the ability to get the next node. So Android Studio, similar to Eclipse, has the tool here to, let's see, where is it under? Generate, getter and setter. And I want to do this for, well, I definitely want to do it for next node. So we'll go ahead and generate the getter and setter for next node. We probably can go ahead and give ourselves a getter for payload. That might be handy to be able to get the value of a node, but we don't need to set the value of a node. It gets set initially. So I'll go ahead and generate a getter for payload. All right, so now we have the ability to get and set the next node, and we have the ability to get the payload. And we could have written those functions ourselves. There's nothing special about these functions other than they use poor syntax by putting the curly brace in the same line as the guy above it, but it's more of a personal pet peeve. You know, these are simple one-liners. Get me access to this private member. So we had to wrap it in a function. All right. So now we have the ability to do that through a node. We can have a node. We can ask that node to set his next node to something. We've given it that ability. Okay? So what we'll do in this else is we'll say n dot set next node equal to this dot head. So n, your next node, is the same thing as head points to. So what we just did right there is this. N was just floating out here. His next node was null. We set his next node to point to the same place head points to. We did that. Make sense? So now we got two tethers on this dude. Now we're free to say head is now equal to n. And that will add it to the front. Make sense? That does this move. So if my list currently looks like this, and we want to add to the front, first thing we do is we make n point to the same place as head points to, then make head point to n. It doesn't matter where this guy lives in memory. It doesn't matter where this guy lives in memory. They very, very, very likely do not live next to each other in memory unless it was just a lucky roll of the dice when we asked the operating system for some RAM and it gave us two buckets next to each other. But we can still get to this bucket by first going to this bucket, following his next node to get to this guy. Front is head. Head always points to the beginning of the list. That's by definition for a linked list. The variable head, which is like in the traditional linked lists, head is the variable that they all use. That's the name of it. If you looked in a data structures book, and that always points to the beginning of the list because we have to keep track of the beginning of the list since we're not relying on contiguous memory. We got to be able to get to the front so that we can traverse to the other stuff. Okay? So that's add front. So now we know how to add front to the empty list and also add front to the non-empty list. Well, let's look at the harder stuff for the display. So here's display. If I have nothing in there, it's the empty list. What if I have something in there? Well, that's the harder stuff. If I have something in there, I probably want to ask a node to display itself, right? So maybe tell a node how to display itself. Maybe a node displays its payload, but then also have a node show its next node. So what we'll do is we'll build into node public void display. And what display will do for node, and this is all text-based stuff, so it's, you might modify some of this for your homework, but this is more just testing to make sure our data structure is working. Okay, so what is display going to do? Display will display this current payload, and then either point nowhere or show the next node. So we'll go ahead and we'll do a system.out.print. I'm doing just a print so it looks a little nicer. So it kind of like is this number with an arrow going to this number with an arrow going to this number. So it looks more like a listy thing. So we're going to print out this dot payload concatenated with, we'll do a little arrow looking dude like that. So payload followed by an arrow. And then we'll say if this dot next node is not equal to null, then we'll say this dot next node dot display. Make sense? And for formatting reasons, we can say else system.out.println. Print out the empty string, that'll kick it down a line. That's the final end. So this else will only get called when we get to the very last node in our linked list. I'll show you how that works here in a second. So we go back to linked list here. No, because it's actually, it'll make sense here in a second. But there is a loop. But the loop is walking from node to node to node. So you'll see it when we walk through the code here. So the harder stuff here is just to say this dot head dot display. So we say that's harder stuff, but that actually looks pretty easy, right? This kind of starts the ball rolling. So in a list that has more than nothing in it, so we go to this guy, head points to something. So what do? We say head display yourself. And what does that guy do? He displays a 4 followed by an arrow. Then he asks the question, is my next node equal to something? Does 4 point to something real? It does. So what does he do? He tells his next node to display himself. That's the loop. So rather than being in a for loop, he just says, okay, I'm done displaying myself. I know I have a guy next to me in line. I'm just going to ask him to display himself. So now this guy displays a 3 followed by an arrow. Then he says, does my next node point anywhere? The answer is no. So what does he do? He just kicks it down the line. He prints out the empty string with the println, so it goes to the next line. So the linked list, I call this kind of pseudo recursion. Each node tells the next node to display itself. It's the same function, the same display function, but it belongs to a different node. Right? So if we're in this big list here, I'm the head of the list and it kind of snakes around like this. I'll display myself, then an arrow, and tell her to display herself. She'll display herself and an arrow, then tell her to display herself. You'll display yourself and then an arrow, then tell you to display yourself. He'll display himself followed by an arrow, then he'll tell him to display himself. You'll display yourself and realize that there's nobody after you, and you're done. You're the one who presses enter at the end. So we still had the loop kind of thing, but it wasn't done through a loop. Does that make sense? So now what we can do is inside of our main activity, just to test this a couple times, and we'll mimic what we've done here. So we've done, originally we added a 3 and then we added a 4 to the front. So we'll do ll.add front 3, ll.add front 4, and then we'll display it. And it should display a 4 followed by a 3 with some arrows in there. Right there. Make sense? All right. Not too bad. So again, this is almost like it's a microcosm of what we talked about in class today. This idea of linked lists has been around for a long time. And a lot of people find linked lists kind of difficult because they're intimidating because now, oh, I'm working with memory and stuff. Memory is only intimidating because you think about memory and you think about crazy looking hexadecimal addresses, and it's scary. This is just a little string that's attached to this guy. Don't let him go. The only thing that's important about pointer, from a linked list implementer perspective, I really don't care where in memory these guys live. It wasn't my job. The new keyword did that work for me. You know, when I came in here and I said, inside the linked list for add front, when I said node n equals new node, this dude's 100% in charge of where the memory is. I don't care. It doesn't mean anything to me. Okay? All I know is he's going to put that node somewhere, and he's going to throw a rope to me so I can hold on to him. Okay? That's my pointer. I'm pointing at him. And I don't want to lose it. I mean, the word you used earlier is a very accurate term in programming. You said reference. You lose the reference to that. I tend not to use that term when I'm teaching it. I try to use things that are more tangible for people. You know, a rope's attached to something or something like that, but you use the correct programming term. This is a reference to that variable. So pointers are memory references, all right? But that makes it start sounding scary again, right? Where if the new keyword just threw me a string and said, don't let go, and it's hooked onto that guy over there, we can understand this. I don't care what his actual address is. I just know I can get to him by following the string. That's all that's important. Okay? The locations in memory just makes things scarier. We don't care. They're in there somewhere. It wasn't my job. It was beneath, or maybe it was above my pay grade. I don't know. But it wasn't my job. All right? So in any case, when we look at node, this is obviously a pretty simple class here. I mean, most of this is just getter setter fluff, right? I mean, what is a node keeping track of? 2 little pieces of information. The value it holds and where the next guy is. The string leading to the next guy. Payload's the value. That's my 3 or my 4. Yeah, I'm choosing the word payload because that's what, similar to the head variable, payload is what most data structures textbooks refer to the value that a node holds. So I'm using kind of those traditional names, but it's the number you're storing. That's what it is. So if you really want to use a different variable, it's fine. That's just a variable name. All right, so I'm keeping track of my value, and I'm keeping track of the string that leads to the next guy. That way he doesn't float off. All right? And then here's my little constructor, just setting those couple of values. So I get my value for this dude, I go ahead and set it, and then make sure that my current next node goes nowhere. I don't have any friends yet. Somebody else will hook me up to a buddy. It's a buddy system, okay? Then we did the little display thing. That's, more of just frivolous stuff for testing it. And then these 3 functions down here are just one-liner getter setters. So even though we have several lines of code here, a lot of this was generated for us, right? By us doing generate getters and setters. Meaningless code. So this is, not a very complex class here. We call this a simple class. Same thing with linked list. We're keeping track of one variable for a linked list, where the head of it is. The constructor for this guy, pretty simple. Just sets head to null. So add front, not a whole lot going on here either, right? Really, we just did two little mechanical moves that all involved as like a little puzzle. How to hand off strings. Okay. Set ends next node equal to head first, then update where head points to. These two lines had to be in this very specific order. Because if we did them out of order, we would have lost, as you pointed out, the reference. We would have let go of the balloon. The string would have floated away. whatever, however you want to visualize it, we lost it. So we had to do those in that order. Okay? And then again, display is more just for testing. So this whole data structure we have implemented at this point really is fairly simple. There's not a whole lot to it. The most important part is how we're using these pieces together. Right? We've got simple little Legos laying on the table here. Now we just have to use them together in an interesting way. All right. Now, what if we wanted to write add end? Okay. Now, I will tell you that in more complex linked lists or in higher performance linked lists, what is often done is they keep track of actually two different positions, the head and the tail of the list. All right. And in those same linked lists, typically nodes then become a little more complex. Nodes don't only know about the next node, they also know about the previous node. So that gives us a little bit more maneuverability within a node. Because you can actually go to the beginning of the list and move in, or you can go to the end of the list and move towards the front. But we're not going to write that one. We're keeping it simple. So we don't know about the tail. We're not going to keep track of the end of the list. We could, wouldn't be very hard at all, but we want to practice this idea of traversing our list. Okay? So if I want to add something to the end of my list, so let's go ahead and just grab a new, so we'll add a 7. So I want to add 7 to the end of my list. Well, the trivial case is if head is equal to null, then what do? Just add the 7. Head points to 7. If head is null, it's the empty list. Adding to the front, adding to the end, same thing. Right? Let's write the trivial case here. So if, we'll go ahead and node n is equal to new node payload. If this dot head is equal to null, this dot head is equal to n. That's the trivial add end. Nothing in the list, adding to the end, same thing as adding to the front, just make head point to that guy. Otherwise, we're adding to the end and we're currently in the list where there is stuff. So for instance, it might be the list that looks like this. Head is not equal to null, it points to something real. In order to add the 7, where would the 7 ultimately go? The 7 gets added to the end. So we need to do that. Real easy if we're just messing around with pointers using human eyes. But the better question is if I only have access to head, how do I get to the last element in the list? I have to walk there. I have to go from here to here. Does that make sense? How do I know that I'm at the last node in a list? Yeah, whenever the next node is null. So when I arrive at a node, like, hey, buddy, where do you point? And he says, I don't point anywhere. Then I know you're the last guy. So guess what? I got a new buddy for you to point to. That's what we're going to have him point over here. But we got to get to him first. So Now, does that mean we go from here then to here like this? What did we just do there? Who points to this guy now? We let go of the string. Can't do that. And we also want to make sure that head always points to the beginning of the list. So we're not actually going to use head for doing this. We need to create a second pointer. So maybe we call this guy curpause, something like that. And we start curpause off at pointing to the same place head points to. And we ask the question, is your next node something? Does curpause point to something real for his next node? Yeah, this guy points to this node over here. If so, curpause equals curpause's next node. Now we ask the question again. Does curpause's next node point anywhere? Does not. I'm at the end. So what do? Curpause.set next node to end. So I'll say node curpause is equal to this dot head, while curpause dot get next node is not equal to null. Curpause is equal to curpause dot get next node. So we'll go ahead and make curpause point to the beginning of the list, just like head points to. They both point to the same place. Then, as long as curpause's next node is not null, make curpause, update curpause to be whatever his next node is. Walk to the next node with curpause. As soon as I get to this line, we know that curpause is pointing at the end of the list. We know it's at a dude whose next node is equal to null. We know we failed that Boolean expression. Right? So curpause's next node must be equal to null. Therefore, what can I do? I can say curpause dot set next node to end. Walk to the end of the list, set that guy's next node to the new node we just built. Make sense? All right, so now we go back to our main activity. We can go ahead and let's do a ll.addEnd, and let's add a 2 to the end. So now we're adding a 3 to the front and a 4 in front of that, and then a 2 at the very end, so it should go 4, 3, 2. There's our 4, 3, 2. Okay. What if we wanted to write remove front? So continuing with our manipulation, we want to remove something from the front of a list and maybe return the value. So if my list looks like this, and I want to remove the front of the list, that means I want to disconnect this 4 from my list. Now I can't just do that, right? 4 is the head. Head points to 4 right now. Well, head, yeah. The front of my list is where head points to. Yeah, so head always points to the head of the list, the front of the list. So when we say remove front, I want to remove this guy. But I can't just do this, because if I do that, I've lost track of this dude. This curpause is currently not in this function. We're in a different function now. So how do I detach this guy while still keeping the list intact and then ultimately return the payload I just removed? So you want head to go to the same place that 4 attaches to? What did I just do there? Lost 4. I want to be able to return 4. So I can't do that yet. I'm also going to need to detach 4 from here. We don't like that. Even though it would get automatically garbage collected, we don't want to have any loose ends. So we want to detach everything. We want it to be a clean break. So what we're going to need is another pointer. We'll call this guy temp. We'll make temp point to the same thing, place that head points to. Then we can have head point to head dot get next node. Then we can say temp dot set next node to null. Then we can return temp. So we kind of strategically disconnected it. All right, so let's. Because we're returning it as well. We're disconnecting it, but also returning the value. If we were not returning the value, we could just disconnect it, but even then, we then have that issue of it's good programming practice to disconnect all loose ends. We still need to actually disconnect the 4 from the 3, even though it should get taken care of for us once 4 gets automatically garbage collected. But I like to teach that we should disconnect it ourselves. Don't rely on that happening. So we come back in here. We go to, we'll do remove front here. So public, we'll have it return an int for our payload. Remove front. All right. Now, in this case, we'll maybe ask the question, if this dot head is equal to null, that means we actually don't have a front. So this is actually an error, correct? So we really should only call this guy if we actually have something to remove. Okay, so we can either do error checking or just make sure we call this guy under the right conditions. I'm going to say let's call this guy under the right conditions right now, just so I don't muddy the water with error checking. Let's focus on just the data structure logic. All right, so we'll assume that we always have something to return here. So I'm going to say node temp is equal to this dot head. So now we have 2 pointers that both point to the same place. Then I'll say this dot head is equal to this dot head dot get next node. So we'll make head point to the next guy after we've preserved the current guy inside of temp. Then we'll say temp dot set next node to null. That fully disconnects it. Then we'll return temp dot get payload. The value of the node we just removed. So if we go back here to main activity, we'll display it. Then we'll go ahead and do system.out.println ll.remove front. We'll go ahead and remove the front of the list, which should be a 4 in this case. 4 is the front of the list. And then just to prove it was removed, let's just do an ll.display again, showing that our list is now 1 shorter. Should have a 3 followed by a 2. So here's 432. We removed front. There's our 4. Displayed the list again. There's our 32. All right. Similarly, what if we wanted to remove end? So if our list looks like this, and I want to get rid of this 7, how do I do that? Okay. How do I attach it to the 7? Okay, I really need to get here. I need to get to the node whose next node has a next node that's null. I need to get to the dude who's right before the last node, because he's going to be my new last node. Once 7's gone, 3 will be the new next node. That makes sense? So I'll start cur node off at head. Now, at this point, we know that we have at least one value in here. But what if there is only one value? What if head points to null? That's a special case, isn't it? If head points nowhere, I mean, head can point to a node, but if that node points nowhere, there's nowhere to traverse. I just need to remove head. I'm dealing with a one list. So I'll ask the question in here. So let's go up here. We'll do remove end, public int remove end. Okay, we'll ask the question if, again, we're assuming that anybody who's calling this is calling it on something it's not the empty list. Okay, so we have at least one element. So we'll say if this dot head dot get next node is equal to null. So we know head is a thing, but it might be that head's next node doesn't actually point anywhere real. And if that's the case, then we'll just say this dot head is equal to null. But I need to be able to remove it. So, or I need to be able to return it. So what am I going to do? Since I just need a value to return, I'll go ahead and say int val to return is equal to this dot head dot get payload. Then I'll say this dot head is equal to null, and then I'll return val to return. That's if it's the one list. If it's not the one list, it's at least the two list. All right, which means that if it's at least the two list, I have the capability of getting to the position that's right before the last node. So I'll say node cur node is equal to this dot head. Then I'll say while cur node dot get next node dot get next node is not equal to null. So while the current node's next node is not equal to null, I know I need to shift forward at least one. So we'll say cur node is equal to cur node dot get next node. In this case, yeah, because if I want to remove this dude, I can't get there and remove him. I need to get here to remove him. Because I remove him by disconnecting him from there while keeping track of him for the value to return. It's this guy that I need to hinge on in order to get rid of this guy. Because if I get all the way to the 7, I'm hanging off the end of the list. It's like, how do I remove myself? I can't go backwards. I don't know about the previous node. I can't scream back and say, just drop me. I can't do that, even though it's funny. Later, Rob. I can't do that stuff. So I need to get here so I can wave at my friend and let go of the later, right? All right, so this will take cur node to that position right before the last node. So once we're there, what do? We'll say int val to return is equal to cur node dot get next node dot get payload. That's the integer we're going to return. Then we'll say cur node dot set next node to null. Let go of the string. Then we'll say return val to return. Make sense? So testing that one real quick. Let's see. So we did a remove front. Let's just do a remove end on this one, just for testing on that side. So remove end, we should have a, let's see, a 3 on the front, a 4 on the front, a 2 at the end. So remove end should print out a 2, and then we should display 4, then 3. So here's the full list, 4, 3, 2. Remove end gives me the 2. New list is 4, the 3. All right, now let's look at our homework assignment here. All right, so we're going to implement our own linked list. So we can't use the third-party built-in one, like I said. So I've given you a starting point for a linked list, and I've even given you the correct starting point for this homework assignment. All right, then implement a class called huge integer that represents arbitrary size positive integers and supports addition only. All right, so what I mean by arbitrary size is infinitely sized. I can hold the number 121, or I can hold the number with 500 digits in it. Okay, but it only needs to be positive. You don't need to support negative numbers. That makes it a lot easier. All right, so we're representing whole positive integers as a linked list of ints. Make sense? So it's going to be a class called huge integer that is going to be a linked list of ints. Okay, you may only use the tools you've introduced in class. You may not use Java's big integer class or anything like it. Because guess what? Java's big integer class is their version of huge integer. Right? That's how it's implemented. So we're implementing something that they've already implemented. Can't use it. So we're writing our own huge integer. Your implementation should support the creation of positive huge integers of any length. You should then be able to add those huge integers together, producing a new huge integer. Create a simple Android interface for the huge integer addition only calculator. So you should be able to maybe type in a whole bunch of numbers. 138. When you submit that, it's going to create a huge integer out of 138, which will be a 1 linked to a 3 linked to an 8. Make sense? Then I'll add another number, 246. Be a 2 linked to a 4 linked to a 6. Then I'll be able to add those two together, and I've already forgotten what my first number was. So whatever the two of those guys added together is, it should produce a new huge integer, which is the solution of the sum. So 100 plus 200 should give you the huge integer of 300. 3 linked to a 0 linked to a 0. Make sense? So only positive numbers and only has to support addition. That makes it way, way, way easier and allows you to focus on the linked data structure aspect of this. Now, right off the bat, you're going to feel like this is harder than it is. I want you to think back to what we did today in class. How we converted a string representation of an int, of a number, into the number itself. We know that the far right position, the end of the list, is the ones place, the tens place, hundreds place. Think about how the numbers work. And you'll find that you can move through these guys without too much trouble. You may find it, so here's a little hint. Because right now, I mentioned in here that some more complex linked lists allow you to go both directions, like previous nodes. You might find it handy to either take that step and teach each node how to get to the previous node, or maybe the simpler solution to this is build your huge integers backwards. So 132 is a 2 linked to a 3 linked to a 1. That way the far left is the ones place. And you know where the beginning of the list is, that's head. Make sense? I think you'll find it easier to write this if you build your huge integers in reverse. Or at least give yourself the ability to reverse itself. But I think building them in reverse will be easier. All right, questions about that? So that's the programming assignment. The report is going to be foreshadowing to next week. So we're going to write a 2 to 3 page paper discussing stack data structure in terms of how it works, It's 3 specific functions and how modern programming languages use a stack to implement recursion. Then finally give an example of a problem for which a stack is the right tool for the job. So this is 2 to 3 pages, could be double spaced. Take it to the writing center. I care more about non-broken English, accurate information than if it's 2.5, if it's 1 3/4 pages instead of a full 2, but it's good written work. I'm more okay with that than 5 pages of crap. Make sense? All right. You'd be happy to know this used to be 3 to 5 pages, but I reduced it to 2 to 3 pages because I'm nice. Probably too nice. None of you think I'm too nice. Talk to me next week. Okay, questions. I'll actually, before I forget here, let's go ahead and push this guy. So we will import into version control. This is homework 2 template. Share. Initial commit. Not for week 1, no. Figured you were getting used to GitHub and stuff like that, so. All right, so there's that project up there. I'll go ahead and throw that on Slack here. So that'll be your starting point for the homework, and I'll get the assignments unlocked on the website. Questions, comments, concerns, bribes? Bribes. It depends how desperate you get. All right.